Hello, College Algebra, and welcome to our third video on 5.2, Applications of Exponential Functions. Today we're going to be doing part 3, and part 3 is going to be talking about exponential, well not exponential, part 3 is going to talk about population growth. And to be more specific, population growth is the increase in the number of individuals or certain species of an animal in a population. People study this to help repopulate endangered species or to control the overgrowth of species. Like, for example, there are certain fish and also tigers are considered endangered species, so there are people that use exponential functions to calculate how long it will take to help the population regrow. Deer, on the other hand, we kind of have an overgrowth over them, so sometimes we'll use population growth to determine how we can keep their population under control. That's where you hunters out there, that's where you guys play in. You play a good role with that. But anyway, we'll be looking at some mathematics behind population growth. So let's say we have a typical hawks example. It says a certain species of fish is to be introduced into a lake, and wildlife experts estimate that the population will grow according to this equation, where t equals the number of years. Given this equation, we're given that we need to find the doubling time for this population of fish. Okay, that was a lot of information at first. Let's first, before we solve the equation, let's look at what formula we're given. We're given that we have 889, and we're going to multiply that by 2 to the power of t divided by 2, where t is the time in years. And that's going to be equal to p parentheses t. Now let's talk about what these numbers represent. Let's first start with the 889. That is the starting number of fish. So in other words, this is the number of fish that they're putting into the lake. This represents how much the population has grown. Or in other words, basically how many fish is in the lake now after so many years. So in other words, this will be the new number of fish after so many years have passed by. And then this part is the growth factor. Basically, this is the number that determines how fast or how slow the fish will repopulate after so many years. So that's all there. I just wanted to show you what each part represents. But now let's use that equation for the actual problem that we have. So now the question is, what is the doubling time for this population of fish? Now, if you're not sure what doubling time means, well, it's basically saying we're finding some sort of time. It's going to be months or years or something like that. We know that much. We're trying to find some sort of time. But the doubling time represents basically how long it's going to take for the population to double in size. So in other words, if this is our starting population of fish, we want to know how long it's going to take for that population to double. Well, let's first figure out what is double that population. Let's check out the calculator. So we have 889 fish. If we wanted to double that population, we'd multiply it by 2. Whoops, that was weird. We want to multiply it by 2. And if we multiply it, we get 1778. So in other words, we want our new population to be 1778. And if we plug that into our equation, where this is the starting population, this is double the population, we just need to figure out how long is that going to take? How much time will it take for our starting population to double to this? So with that in mind, you basically have an equation that you have easily set up that you can solve. Well, I guess we'll start with the easy stuff first. Probably the easiest thing to do to solve is let's take care of the 889. Since the 889 is being multiplied, the opposite operation would be to divide it to both sides. So this would cancel, and that would just leave you with 2 to the power of t squared on the right. On the left, you'll do 1778 divided by 889, which if you put that in your calculator, that should give you 2. So that's what we get so far. So we get 2 equals 2 to the power of t. Okay, I'm not sure how I'm going to get t from this, but we might be able to use something that we've already learned. What if I take the 2 on this side and I raise it to the power of 1? You know this is true because 2 to the power of 1, that's still 2. That checks out. But why would I want to do that? Why would I want to rewrite 2 as 2 to the power of 1? Well, check it out. Check your bases. Your bases are the same. And if you remember from a previous lesson, if your bases are the same, that means you can take the powers and set them equal. Or in other words, take 1 and set that equal to t divided by 2. And now all you gotta do is figure out what t is. Some of you can probably easily look at that and figure out that what the time is. If you're not quite sure what the time's going to be, what you can do is rewrite 1 as, well, 1 over 1, and then just cross multiply. Do 2 times 1 to get 2, and then 1 times t to get t. And there you go. You're given that the time will be 2 years. It'll take 2 years for this population of fish to double to 1,778 fish. And that's it. That's the typical type of equation wildlife experts will use to calculate population growth. Let's try another one similar to that, just so you get the hang of it. So here we still got the same species of fish. We still got the same equation that our new population of fish will be equal to the starting population of fish times 2 to the power of t divided by 2. But now look at the question, step 2. How long will it take for the population to reach 3,556 or 3,556 fish? So this time it's not asking for the doubling time or the quadruple time or triple time or whatever. It's giving you a specific amount. Basically, it's saying, hey, what if we want the new population to be 3,556 fish? How long is that going to take? How many years will it take for the population to reach 3,556? That's it. You literally just plug in 3,556, and then you chug away. So this one, very similar. First thing we'll do to solve for t, let's go ahead and take care of the 889. Since it's being multiplied, the opposite operation would be to divide it to both sides. So then this side, that's gone. On the right, you'll still have this. You'll still have 2 to the power of t over 2. Now let's do 3,556 divided by 889. Let's go ahead and put that in our calculator. So clear 3,556 divided by 889. So that gives us 4. So that divided by that will give you 4. So now that leaves us with 4 equal to 2 to the t over 2. Sadly, fortunately, the bases are not the same. However, what if we rewrite 4 so that it does have a base of 2? For example, the 4 could be rewritten as 2 squared. Now that is a big help. If you rewrite the 4 as 2 squared, now the bases are the same, and now the bases are the same, you can set the 2 powers equal. So you'll have 2 equal to t divided by 2. Solve for t. Rewrite this as 2 over 1 and cross multiply. 2 times 2 will give you 4. 1 times t will give you t. So t is equal to 4 years. It'll take 4 years for the population to get to 3,556. And there you go. Just basically using stuff that we've learned before about making the basis the same and saying the exponents equal. You're just now seeing it in a real life example. How about we do a couple more examples like that using similar stuff, and we'll go from there. So now, a certain species of deer, not our type of deer, we're talking about deer in Africa. For example, there are some endangered species of deer in Africa. They are to be introduced into a forest, and wildlife experts estimate that the population will grow according to that equation, where t is years. And given this information, we need to find the quadruple time, or the quadrupling time. So, let's write down the equation we have. The population is going to be equal to 206 times 4 to the power of t divided by 2. Well, this time, 206 is our starting number of deer. And then, of course, this will be the new population of deer. And this time, we are trying to find the quadrupling time. Of course, we're trying to find a certain amount of time, but in this time, instead of double, we're quadrupling. And quadrupling, if you remember, that's times 4. So we need to find 4 times, or we want the population to increase by 4 times as much. So let's go ahead, let's find out what 4 times our starting population is. Okay, let's go to here. So clear 206. We're going to quadruple that, times it by 4. It's going to be 824. So in other words, we want the new population to be quadruple the starting, which is 824. Equal that to 206 times 4 to the power of t over 2. We just need to figure out how long it's going to take. How long is it going to take for the deer to repopulate to 824? So there you go. You got your equation. Now you can just plug and chug. So here, let's go ahead and do the easy stuff first. The 206 is being multiplied, so we can divide it to both sides. So then on this side, 824 divided by 206, that should get you 4. And then on this side, you still have 4 to the power of t over 2. On the left side, I'll rewrite that as 4 to the 1. And lucky for you guys, the bases are the same. So that means you can take the exponents equal to each other, and that means you can easily find t. So for the 1, rewrite it as just 1 over 1, cross multiply. 2 times 1 is 2, 1 times t is t. So it's going to take the deer 2 years to quadruple their population. Piece of cake. All right, one last example. This one's going to be interesting. So we still got the same species of deer. We still got the same population equation. So 206 times 4 to the power of t over 2. But now let's read the question. How long will it take for the population to reach 843,776 deer, according to this model? Ooh, that is a big number. So in other words, we want our new population to be 843,776. And we need to figure out how long that's going to take. Some of you are probably thinking, that's a big number. It's probably going to take them a long time to repopulate, like that fast or that big. Well, let's find out. Let's find out how many years. So, all right, so we're going to do the easy stuff first. Let's divide by 206 to both sides. So then on this side, I still have 4 to the power of t squared. And then we got to do 843,776 divided by 206. So 843,776, divide that by 206. What does that give us? 4,096. Woohoo! So we have 4,096 equal to 4 to the power of t over 2. And yeah, that's not the same base. And some of you probably can't think of what this could change into off the top of your head. So yeah, we need to try and remake this a base of 4. Maybe we should try multiplying 4s first. So I know 4 times 4 will get me 16. Multiply that by 4, that gets me 64. Still not high enough. So let's do another 4. Another 4 will get me 256. Still not big enough. Multiply by 4 again. That will give me 1,024. Let's try one more time. And that gives me 496. That's what we want. So we got to multiply 4, 1, 2, 3, 4, 5, 6 times to get our base. So in other words, 496 is the same thing as 4 to the power of 6. And then that's going to be equal to 4t over 2. And if you need a double check, let's go to our calculator. Let's type in 4 to the power of 6. So 4 to the power of 6. And that is 4,096. That's exactly what we need. And that works for us because the bases are the same. And thus we can set our powers equal. So 6 equal to t over 2. We write the 6 as 6 over 1 and cross multiply. 2 times 6 will give you 12. 1 times t will give you t. So t is 12 years. Well, it's definitely a lot longer than some of the other species, but it would only take 12 years to have that many deer? Holy cow. Whew, that's actually, personally, I don't think that's very long, especially for that big a number. Whew, someone's got to keep that population under control. But anyway, I think you guys got the handle with these type of equations. Population growth equation should be easy for you guys. And that covers up 5.2. Though, I will warn you, there will be some different types of problems in the online homework that I did not cover in the packet. Please do not freak out. I have covered all the hard ones in these videos. The rest are going to be easy plug and chug problems. So if you come across an example that I did not cover, in other words, it's covering a topic that I not teach, or in other words, it's a question that's not over radioactive decay, if it's not over compound interest, if it's not over revenue, if it's not over population growth, it's over something completely different, don't worry. That type of problem, it will give you the formula, it'll give you exactly what you need to plug in. They're literally just normal plug and chug problems, so don't worry. I covered all the hard ones. All the rest are plug and chug. Just wanted to let you know ahead of time. But with that said, you guys are officially ready to start your 5.2 online homework. And again, if you have any questions or concerns, email me or contact me via Google Hangouts. And I'll see you guys later.